Hey there, Mustangs. Welcome back to another edition of No Here, No Problem. I'm in my basement where it's really cold and it's cold outside, so I'm freezing. So I figured I'd wear my Snuggie and make this video for everybody. But we're going to be doing the video for the review for Chapter 6 on this. And I'm going to kind of go quickly. So, again, if there's some part of it that you want to skip, skip it. If there's some part that you want to go back and watch again, then go ahead and watch again at your discretion, okay? Let me go ahead and minimize myself here to get myself out of the way as usual. And we will go ahead and get moving here. So the first thing that we're talking about here when we're looking at functions is there's several rules we actually reviewed in this unit, okay? And in this first section here, 6.1, we talked about the domain. Now remember, domain talks about all of the values for x that exist. And you'll see that in some of these problems here, things are highlighted. That's because there's only 2 times that we ever encounter any sort of domain restrictions. Those domain restrictions happen when we have a square root, and they happen whenever we have a fraction. Okay, that's because on the inside of our square root right here, we cannot have a negative. Okay, we don't want a negative because if I take the square root of a negative, we end up with an an imaginary number. When we look at a fraction, the denominator cannot equal 0 because I can't take a number and divide it by 0. If I do, it becomes undefined. So that means that any other situation whatsoever, there's going to be no restrictions. And that means that your domain includes all of the values for x that exist out there. So if we look at number 1, this is a prime example where there's no square root and there's no fraction, therefore there's no restrictions. Okay? And because there's no restrictions, therefore the domain is all numbers exist, so it's all real numbers or negative infinity to infinity. Okay? Take a look at number 2. Number 2 is a situation where we actually do have a square root involved. That square root that we have right here cannot be a negative, right? I cannot have a negative. It could equal 0, because I could do the square root of 0. That equals 0. I could do the square root of a positive. That's going to equal some positive number. But this right here is going to equal some imaginary number, and we don't want imaginary numbers. So what we're going to say is that x minus 1 that's inside of there, it can't be negative. It can be a 0 or positive. So this symbol says right here, when you look at this, it's going to be greater than 0, which makes it a positive. And it can be equal to 0, because we said it's okay to equal 0. And so if I was to solve for this, we would say that x is going to be greater than or equal to 1. And then that says that our domain, if you think about this in terms of a number line, okay, I have 0 and 1. We can include the 1 because we can equal 1, and it's going to go to the right. So if I start at 1 and I go to the right, the values that are all the way over here to the right are all the way to infinity. So my domain for this is from 1 to infinity. And that's what our graph looks like. So let's see what the graph actually does look like on decimals here so you can understand the concept here. Okay. When we say the square root, let me open this up, sorry. The square root of x minus 1, and you can see that the graph that's taking place here starts at 1 and it goes to the right forever. Okay, there's no values for x over here because if I plugged in a value, let's say it was like a negative 10, if I was to go ahead and do the square root of negative 10 minus 1, okay, you would see it becomes undefined. And if I was to put in 1, you can see if we put square root of 1 minus 1, which is 0, that just gives me 0. So this is where my graph exists, okay? All right, so the same idea with number 3. There's a restriction here because down on the bottom of our fraction, there's a denominator, and this cannot equal 0, right? Because if that was the case, we would have 3 over 0, which is undefined. And so when we look at this, x plus 7 cannot equal 0. And that means that x cannot equal negative 7. So if we think about this in terms of a number line, okay, I can go to negative 7. It can't equal it. It's going to get around it. It can equal everything to the left, everything to the right. It just simply cannot equal. I don't know what happened to me here. I'm gone. All right. It simply cannot equal lost my frame here. Negative 7. And so when we look at this, this is going to go from negative infinity to negative 7 on the left side of it, okay? And we're going to put a parenthesis because I can't include it. And then we're going to pick it up from the right side. It's going to go from negative 7 over to infinity again. And so this is what our domain ends up being for this problem here. And so when I look at my fraction here, what would you say it was? It was 3 over x plus 7. So if I look at 3 divided by, and then x plus 7, you can see that this graph exists everywhere. It's literally exists everywhere. You can see it's over here on the right, and it's over on the left. It's just not right here at this negative 7. Just to confirm it, if I was to say x equals negative 7, you would see that there's this vertical line that my graph gets really close to it from the right and really close to it from the left, but it never actually touches it, okay? And if I was to put in that negative 7, and I said 3 divided by negative 7 plus 7, you can see we get an undefined value there. Can equal anything, just not negative 7, okay? All right, so now that we have that idea down, let's go ahead and speed up through these a little bit quicker, okay? So the 3x minus 7, it's not a square root, it's not a fraction, there's no restrictions, so it's all real numbers or negative infinity to infinity. Number 5, the denominator cannot equal 0. So since that cannot equal 0, we have to try to solve for it. Well, it's a quadratic, so the methods for solving, we have everything possible that's out there. You have the quadratic formula, you have guess and check, you have square root method, you have the leading coefficients one. In this case, we're going to do the guess and check method. And when I look at the values and I guess and check them, 2 times 1 is going to equal this 2 that's right here, right? 3 times 1 is going to equal the 3, okay? And then when I check this, this gives me a negative 2, and when I check this, this gives me a negative 3. Put the negative 3 and the negative 2 together, we get that negative 5 that's right there. If I solve for each one of these now, we get that x is equal to 3 over 2 and x is equal to 1. So that means it could equal any other value besides those. So it cannot equal 3 over 2, and it cannot equal 1. But it could equal everything over here to the left, everything in between these two spots, and then everything to the right of those, okay? So that means we're going to have 3 different areas where we have to look at the domain. It's from negative infinity, which is all the way to the left over there, all the way up to positive 1. And then we say a u. The u, remember, is the math symbol for saying and. Everything in between 1 and 2. And everything to the right of 3 over 2. So this is what the domain ends up looking like. Okay. Now, if I was to look at this graph, we would say we have, let me get rid of these. We have a fraction, and we have 2x minus 3 over, whoop, I wrote the wrong value there, over minus 3. And then 2x squared minus 5x plus 3 for the bottom. 2x squared minus 5x plus 3. And let's look at this graph. Did I do that right? Plus 3. So it can't equal 1. It can't equal 1.5. Okay. And so, what is it? 2x minus 3, 2x squared minus 5x plus 3. All right, so there's our graph. Okay. And we said that it cannot equal, oh, I didn't even notice that. Oh, there's a hole in this picture. Oh my God, the key has a mistake here. There's a hole, but that's okay. So it can't equal this. What ends up happening is that denominator right here and this, they actually cancel each other out. So this is what we call a hole. And then it's not going to equal 1 either. That's okay. It doesn't change anything. It's just that it can't equal these values. So let's check it right here. At 1.5, x is equal to 1. You can see there's this vertical line right here. Now I'm going to go ahead and graph at 1.5. And at 1.5, I'm going to see if I can trace it out. Okay. Tracing this out right here. I can't get to trace. Hang on. There we go. If I go to 1.5, I want you guys to see what happens here. You see that? It's going to happen quick because it's hard to keep it on that exact spot. But at 1.5, you can see we get a undefined value right there. That's called a hole in my picture. It's not an asymptote, it's an actual hole because I can't have a 1.5 in the denominator, and because it cancels with the numerator, we call that a hole. Okay. For number 6, we have 3x plus 5. That's in a square root, so that has to be greater than or equal to 0. 3x has to be greater than or equal to negative 5, which means that x has to be greater than or equal to negative 5/3. Okay? And so for the domain for that, it's going to be negative 5/3 all the way up to infinity. All right, so that's 6.1. Let's work on 6.2. 6.2 is just function operations, so they should go pretty quickly. There's just algebra involved. So again, if you get stuck, go ahead and just work on the algebra yourself there. But let's go ahead and jump into these here. All right, I got to move this back. Okay. All right, so this first one, when we look at number 7, what this says is when we see this, it says f of g of x. Okay, f of g of x. And so f of g of x implies that what we're going to do is we're going to take g of x and we're going to put it into f of x, right? So it goes this direction. We're going to take g and put it into f. So you have to find your g function, which is right here. And that function is going to go into my f of x for this x right here. So that's going to be f of square root of x minus 4, which means that function is going to look like this. Taking this right here and putting it in for this x, okay, and that's going to leave us still with a square here and a minus 8, which is still in these two spots. So from here, you just simplify. When we simplify, the square and the square root right here are going to cancel each other out. We're left with x minus 4 minus 8. Simplify that, we get square root of x minus, f of x minus, f of square root of x minus 4 is going to equal x minus 12, okay? For number 8, we're going to go ahead and do what it says, which is to do subtraction. So this one says we're going to take the g function, which is right here, and we're going to take the h function, which is right here, and we're going to subtract these two functions. But they're giving me a value of 8 that we're going to actually evaluate this at. So if I do g of 8, we're going to take this 8 and we're going to plug it into the equation that's right here. And so we end up with the square root of 8 minus 4, which is the square root of 4, or just 2. When we do the h of 8 portion of this, we're going to take the 8 and we're going to put it in for this x right here. Okay? And that's going to give me 9 minus 5 times 8. So that means we have 9 minus 40, which is negative 31. And because I have two negatives right here, those will turn into a positive, which means we have 2 plus 31, or an answer of 33. Okay? Number 9. Number 9, when you read it, this says h times f of x. So that means we're taking h of x and we're going to multiply it by f of x. Okay? My h of x function is right here. It's that 9 minus 5x, so that's going to go right here. My f of x function is going to be x squared minus 8, so that's going to go right there. And we're going to multiply all this together. We're going to use FOIL to multiply all this all together. So 9 times x squared, 9 times negative 8, negative 5x times x squared, and negative 5x times negative 8. So there's 4 terms that we should have when we multiply all this together. And again, here they are. There's a 9x squared when we multiply that. Okay. There's a negative 72 when we multiply that. There's a negative 5x cubed when we multiply that. And then we have a positive 40x when we multiply that. So now rearrange it and just put it in correct standard form. It's just going to be negative 5x cubed plus 9x squared plus 40x and then minus 72. Okay. This is more practice of it, so I'm going to kind of speed up the process here. This one says we're going to take f and g and we're going to add them together. So f of x and g of x. F of x is x squared minus 8. G of x is square root of x minus 4. Now these don't actually go together. Because I have that square root on there, I can't put these together. They're not like terms, so we're done. The only thing I would state here is that the domain is that x has to be greater than 4 because we can't take the square root of a negative number. All right, number 11 says we're going to take f and put it into h. So that means we're going to take f of x and put it inside of h of x. So that means we're going to take h of x squared minus 8. So we're going to take the f of x and we're going to put it into the x over here in my h of x. And so when we do that, we have 9 minus 5 times that x squared minus 8. And then we just simplify. H of x squared minus 8 is equal to 9 minus 5x squared plus 40. Simplify from there, we have negative 5x squared plus 49. Okay. This one, we're going to do g of h of 1. So that means we're going to take h and we're going to put it into g. But we're going to evaluate this one as equal to 1. So that means we're going to do h of 1 first. So that means let's take 1 and put it into h right here for this x. Okay. So that's going to say 9 minus 5 times 1. Let's do it right here. 9 minus 5 times 1 is just equal to 4. So now that we know that h of 1 is equal to 4, we're going to take that and we're going to throw it back into and replace this now with what it is, which is 4. And again, we just got that from right here, okay? So from here, let's go ahead and replace the function that's given to us, that g of x function, that's this function. We're going to take a 4 and put it inside of there now, okay? And so that's going to be 4 minus 4, which means that g of 4 is equal to square root of 0, or just 0. Okay? All right, let's go over here to number 13. This one is very visual. It's a graph, so let's go ahead and evaluate the pictures here. This first part, when we look at this, says we're going to find f of 1. So we're going to look at when x is 1, and we're going to look at the f function and get the y value from there. So if I look at the f function, which is right here, we're going to look at where the graph is equal to 1. Well, you can see right here that these goes by ones, right? So if I go to that first spot, the 1 right there, I go to my picture, this is the value that's right there, and we go to the y, and it's going to equal a -5 right there, okay? So that first value of f of 1 is going to be at -5. The next part we're going to do is g of 6. G of 6 is the red function, so it's this one right here, and we're going to evaluate when it's equal to 6. Well, 6 is right here. I'm going to go to my graph, which is right at 6, is right here, and we're going to go all the way over to the y value and look, and you can see that that's a 4 right here. Because the coordinate that's right there at this spot is 6, 4. So when x is 6, y is 4. And so we can pull that up. It's going to be a 4. So we have -5 plus 4, which is equal to a -1. All right. Number 14 is a little tricky, but again, just follow along. It's not too bad. All right. What this says when we look at this is we're going to take this 4 and we're going to put it inside of g. So we're going to evaluate first g of 4. So let's go to our function g. Okay, that's the red function here. We're going to go on this red function, we're going to look at where it's equal to 4, which is right here. And I go to the graph, and this is the spot on the graph that we're looking at. That coordinate right there is at 4, 1. So the y value is equal to 1. So if I go here, we're going to go now f of 1. That g4 is 1. So now let's go to f of 1. So we're going to go to this picture here, and we're going to look at where it's equal to 1. It's equal to 1 right here. Go to your picture, and it's right there is the spot. That coordinate right there is at 1, -5. So the value for this is going to equal a negative. Oh, did I do it? No, I got a mistake on there. It's not -4, it's -5. So there's a mistake on the key right here. So this is -5. Okay. All right. Oops. All right. Next problem. Let's go ahead and look at this here. Let's get rid of this stuff. Okay. This is saying let's multiply the values together. So it's saying f of g of 2. So that means we're going to take the f function at 2. We're going to take the g function at 2, and we're going to multiply these together. So the f at 2 is, this is my f of x. We're going to go to where it's 2, which is right here. And that's the spot right there on the graph that we're looking at. That coordinate right there is at 2, -4. Okay, so that's that spot right there. So that first spot is at -4. Now we're going to do g of 2. That g of 2 is going to be over here. So let's go to 2, and it's going to be right here on my graph is where it's equal. And that coordinate is 2, -2. And so we're going to go ahead and put a -2 there. And then we just multiply them, we get an 8. All right, and then the last question here, for what values of x does f of x equal 4? That means that what we're saying here is, when we're looking at this, we're saying that the y value right here is equal to 4. Well, we look at where the y value is equal to 4, and y is equal to 4 right here. Right? This is the equation for where y is equal to 4. It's right there. Okay? And so it says, when does f of x, so we're looking at f of x, which is right here and right here where they touch. That value right here is at -2, and this value right here is at 4. So -2 and +4. Those are the two spots. All right, 6.3, this was inverses. This should be pretty quick because this is just using basic algebra to solve these. Remember to find the inverse, you take the x and the y and you just swap their places. So take the x and y in this problem, and we're just going to swap the places, and then we're going to resolve for the y. So in order to get the 3 to move over here, I'm going to subtract 3 from both sides. In order to get rid of this 2, I'm going to divide both sides by 2. In order to get rid of the 3 that was right here, I take the cube root. Instead of, if it was a square, we do the square root. Well, with the cube, I do the cube root. And we're left with the cube root of x minus 3 over 2 is equal to y, which is our inverse. Okay. For number 18, same thing. We're going to take the x and the y, so this y, and we're going to swap the x and the y positions. And then we're going to start solving again. To get rid of this 2, we multiply both sides by 2. To get rid of the 18, we move the 18 by subtracting it. And then to get rid of the 2 here, we're going to, inverse of multiplication is divide by 2. And if I take 2 and divide it by 2, we get 1. 18 divided by 2, we get 9. And so this is my inverse. Okay. Number 19, we have negative x squared plus 3. Let's switch the x and the y. Move the 3 over by subtracting it. Divide by negative 1 to get rid of that. And then when we take the square root, we're going to get rid of the square that's right here. We take the square root. We take the square root of both sides, and we end up with plus or minus the square root of negative x plus 3 is equal to y. But due to our domain restriction there, it says we want it to be greater than 0. That means we don't use the negative, so it's going to be the positive instead of the negative. Okay? All right, let's do some more inverse problems, but this time we're going to actually be doing the graphs of both of them. Okay? Switch the x and the y. Move the 1 over by adding it. Get rid of this negative 1/5 by multiplying by negative 5. That's the inverses of dividing by negative 5 is to multiply by negative 5. And so we end up with negative 5x minus 5 is equal to y, which is our inverse. Now, if I graph both of these on one picture, we can see that they're inverses because they reflect over this imaginary line right here. Remember, this line is the y is equal to x. And so every point it gets reflected over this axis to create that mirrored image that takes place when we do find the inverse. Okay. Take the x and the y here, swap the places. The inverse of the square root that's right here is to square both sides. Move this 2 over by adding 2, and we have f of x is equal to x squared plus 2. We look at the graph for this, and this is what the graph of each of these looks like. This is my square root function, and this is my parabola. Now, your parabola actually is supposed to look like this. If you remember parabolas, they always look like this. That's that x squared function. But what this portion of the graph says is we only want it to exist when x is greater than 0. So that means that we take this part that's right here, and since it's less than 0, we just get rid of it, and we keep just the right side of that, and that gives us that mirrored effect that we were looking for. Okay. 22 is a little bit of a doozy, but it's important. You guys can easily do this. What we're doing for this one is you're taking each one of the points that's given to you in this problem, and you're just flipping the points around. Okay. So if you look at your picture, the very first point that was given to you is right here at 2, negative 4. In order to find the inverse of this, you just swap the positions and it becomes negative 4, 2, which is over here. The next position in this was at 4, 0. I'm sorry, no, it's not. The next position was at negative 1, negative 2. Swap those points and we get negative 2, negative 1, and that's going to be over here. And then, as I was telling people, connect it. Immediately connect it. So from blue to red, it's connected. So from here, blue to red is connected. Okay. The next thing we're going to do is this 4, 0. Okay. Let's go and reverse it. We get 0, 4. And then immediately connect it to the next spot. That way we don't lose track of where we're at. And then the last point in this was at 3, 3. And if I took 3 and 3 and flip it, it goes to 3 and 3. And therefore, it doesn't move. So this is my reflected graph of this original graph that we see right here. It's reflected over this line right here. So you can see if I put that line right there, there's a reflection. It's the same on the right as it is on the left. Okay. All right, let's prove inverses. There's no way around this proof. You have to do the actual proof, okay? And this is one of the questions on the test. To prove it, we have two proofs we have to do. We have to prove that f of g of x is equal to x, and that g of f of x is also equal to x. So what this says is, for the first part, we're going to take this and plug it in for this x. That's doing the f of g of x. And if we substitute it in, we're going to simplify. The 16s will cancel. The 4s will then cancel. And we are, in fact, left with x. If I do g of f of x, that means we're going to take this and we're going to put it in for this x right here. And so we're going to simplify this. The 4s will cancel each other out, leaving with the negative 16 plus x plus 16. And then the 16s cancel each other out, leaving with just an x. Okay, same proof over on this side. Okay, you got to do the biconditional proof. Prove that f of g of x equals x and g of f of x also equals x. And so we're going to take g of x, plug it in over here, and it's going to look like this. The cube and the cube root will cancel each other out. And then 3 minus 3 leaves me with just an x. For g of f of x, we're going to now take this function and put it over here, which will look like that. The cube that is on here, what we're going to do is we're going to first deal with this inside part, the negative 3 plus the 3. And then the cube and the cube roots that are there are going to just cancel each other out, leaving with just an x. So there's your proof. All right, last section here are the vertical motion models. The equations will be given to you. You'll either see this or you'll see the actual equations, so you don't have to memorize that. But you just have to know where things go. So when we look at this problem, it says an athlete throws a discus from an initial height of 6 feet and with an initial velocity of 46 feet per second. So they're giving me information. They're saying initial height. They're giving me that this is the initial height right here. Okay. We're saying that the initial velocity, which is this right here, just throw those into the equation. We have negative 16t squared plus 46t plus 6. So this is a quadratic. We want to try to solve this. And so the question is asking then, so this is an equation. The question is asking, after how many seconds does this discus hit the ground? Well, when something hits the ground, it's not in the air anymore. It's got a height of 0. So we say h is equal to 0 or s of t is equal to 0. If I take that and plug it in, we end up with 0 is equal to negative 16t squared plus 46t plus 6. So now if we were to do all the work behind this, the only way to really solve this is to take the quadratic formula, unless you're really good at factoring. So negative b plus or minus square b squared minus 4ac all over 2a. And then if I simplify it, we end up with two answers. We get a negative answer and then a positive answer of just 3. If I was to take this and throw this into Desmos and graph it, this is what the graph looks like. Now you can see, thinking about what's happening, we have a discus that's starting right here. It gets thrown through the air. It lands on the ground, and it lands on the ground after 3 seconds. It's at a height of 0. And we get this negative right here, which is like if I was to go backwards in time. But what's happening is I'm starting from a height of 7. Okay? So there's that picture. All right, let's take a look at this next one here, a spittlebug. Spittlebug is a little tiny insect, and it's actually pretty cool. It's able to jump like super high. If you see this stat right here, it says, a fun fact, spittlebugs' hind legs are known to accelerate faster than any other insect on the planet. They can actually jump over 100 times their own body length. This is like if a human being were to jump over a 70-story building, okay? So that's like comparing how high they can jump to how high a human would be able to jump, which is crazy when you think about that. So you've got a spittlebug jumps in the air from the ground. That means it's got an initial height of 0 and an initial velocity of 10 feet per second. So just throw those in. And it says, when will the spittlebug land on the ground again? That's going to be when it's equal to 0. So if we put the 0 in, we'll solve. I could factor out a negative 2t. You can use quadratic formula if you want. Solve each one of these. You get that t is equal to 0 and t is equal to 5/8. So that means after about 0.625 seconds. And it says, after how much time will the spittlebug reach its maximum height? Well, the maximum height, if you think about this, is that's going to happen at the max, which remember we talked about this in the last unit. We said the max happens when the axis of symmetry goes through it. So the time is going to be negative b over 2a. That's the AOS. And so we do negative 10 over 2 times negative 16. We get negative 10 over 32, or 5/16 of a second. So after 0.3125 seconds, that's when it's at its maximum height. It goes bing real quick. Well, what is the maximum height? Let's take that 5/16 and plug it into the equation, and we'll get a maximum height of 25 over 16, or 1.5625 feet. So again, think about this. Do you see this tiny speck right here? The tiny speck right here. That means it's going 1.5 feet. So to put that into perspective, I'm going to put right here, 1.5 feet is all the way up here. This is a foot. I'm going to back up a little bit. 1.5 feet is about right here. So that little tiny bug could jump from this spot all the way up here. It's this big, but it could jump that high, which is crazy. If we were to look at the picture for this is what the graph of this looks like, and you can see all the information right in there. That's a spittlebug jumps, it goes up in the air, comes back down. After 0.625 seconds, it hits the ground. And after 0.3125 seconds, it's at its maximum height, which is 1.5625 feet. And that's it. So your test, again, is going to be pretty similar to this. If you understand all those parts, you're in great shape. Ask if you have any last-minute questions. I'm available during our beginning of school just for a little bit, and we could ask some questions before class, right? But you guys take care, be safe, be respectful, be responsible, and you have a wonderful evening.